My name is Aldo Botelli. I'm a Director of Engineering at True Circuits, and I'm here to talk about our DDR PHY IP. First, a little bit about True Circuits. True Circuits is a leading provider of high-performance general-purpose PLLs and DLLs, but also providing high-performance DDR PHY supporting all protocols. It was founded in '98 and headquartered in Los Altos. And we have a experienced analog mixed signal team led by a world-class PLL expert. Our IP is characterized by highly automated circuit characterization and porting platforms, parametric testing for MPW test chips, and in general is easy to use, programmable hard macros that are available in most processes and process variants. We worked with many foundry IP partners, TSMC, Global Foundries, UMC, and our production volumes are in the billions. So today I want to talk about our DDR PHY IP. The differentiating points are that it's a high-performance DDR PHY. It's very simple to integrate, easy to do timing closure on, characterized by a lot of automatic training. It allows you to build a low system cost and is also simple to bring up. So it's high performance because it can reach, for the LPDDR5 protocol, 6400 Mbps transfer rate. The architecture has been proven both for DDR4 and LPDDR5 at 3200, but in 28 nanometer and 40 nanometer, but it can reach higher speeds for other technologies. The tuning performance, it's reached through a set of high-level training algorithms. In particular, we have multi-cycle range, write leveling, read-write data I training, and also some of these trainings happen continuously during mission mode. So in particular, continuous read gate training, continuous read data I training. It's also characterized by low latency. There's no transaction delay required when affecting different ranks, and in general, the PHY can be optimized for the floor plan of the customer to achieve low latency. In general, a very important feature of the PHY is that it's easy and simple to integrate. So we implement the PHY for the specific floor plan of the customer. So normally we receive the I/O characterization, so the I/O table from a customer that wants to implement the PHY in a particular direction, we basically implement our PHY based on the characteristics of the I/O ring that the customer desires. So, and we deliver it with no assembly required as a single hard macro. So in the hard macro that we deliver, so there's included a hardened balanced clock tree that allows the timing between the different components, the hard macros of the components, but it also allows the communication between the hard macros and the soft macro that is usually a narrow interface that communicates with the memory controller. So easy timing closure is achieved through a set of techniques, but can be summarized by mostly using source synchronous clocking. That allows us to basically avoid a big clock tree, avoid the implementation of a big clock tree by the place and route tools, and so it simplifies very much the implementation, the place and route implementation. The PHY is DFI 5.1 compliant and supports DFI ratio of 1, 2, and 4. It's characterized by DFT features like loopback and BIST for the analog macros. It includes a PLL, so it's normally possible to provide just a low quality reference. And it has, of course, characteristics like on voltage regulator for noise sensitive circuits and flexibility on the I/O strengths and termination settings. A little bit more about the timing closure. So the PHY, like I said earlier, is delivered to the customer floor plan as a single hard macro, but is tailored to the specific floor plan of the customer. So the PHY communicates basically with the memory controller through the soft logic, and that handles the training of the hard macros. So our soft logic includes a special purpose processor that basically can be receives a firmware for the training operations, and that allows us flexibility in implementation of the training itself. The PHY provides the clock for the memory controller normally, and normally that happens with a divide ratio of the PHY ratio, so that basically the timing closure of the memory controller and the soft logic is simplified by the lower frequency. Soft and hard clock domain are traversed through employing sort of synchronous clocking, like I said, and so that allows us to basically move data between the soft macro and the hard macros through sort of synchronous interfaces and asynchronous FIFOs, and the synchronization between the hard macros happens using our hardened clock tree that is included in our hard macro as a hard macro. Like I said, there's a lot of automatic training that the PHY performs. And this is driven and managed by a lightweight special purpose processor. Just to mention a few, we have multi-cycle write leveling, multi-cycle read gate training, and then in general for each single per pin DQ, we can have optimized read data I training, including the 5 VRAF, and write data I training, including the memory VRAF. During read operations, we actually continuously calibrate this quantity, and also CA can be trained both on the timing side, on the delay side, and on the VRF side. This slide just illustrates continuous training. So in this simulation, we just modeled dynamic components of delays, and actually it's a superposition of dynamic components of delays. Each one is different for every single DQ, and just the simulation shows how the delay is tracking the delay. The delay of the PHY tracks the delay that is modeled in the simulation for this implementation. We claim that it allows to build a low system cost because automatic training compensates for the skews in the system, so you can lower the package and the board cost. And in general, it gives you a lot of visibility on the system timing and the state, and this allows extensive simplification of the debug operations in the lab and in the field. We also have measurement capabilities, so we can collect information about jitter. We can override the system parameters, of course, and we can control the training through software. We can bypass the PLL in case this is all necessary. We also take care of a silicon validation for the test chips that we implemented, and we have implemented a highly automated test and characterization environment. So that allows us to validate the system timing compliance, but also characterize the robustness of training across the PVT variations. So this way we can validate the trainings and the necessity of periodic training of the PHY. This support for validation can also be offered to customers. This is a picture of our silicon test boards, and in general, here's a summary of the characteristics of this DDR PHY IP. It's a complete scalable high-performance DDR system, fully automatic and managed managed by a lightweight special-purpose processor. We have continuous tuning for read gate training and read data I training. It's delivered as a single unit, single hard macro, but it's implemented as a tailored implementation for the customer floor plan and the I/O placement of choice of the customer. It's easy to do timing closure because we're using source synchronous clocking, characterized by DFT features like loopback and dist. PLL is included. It allows you to lower package and board cost, and it features characteristics that simplify debug and bring up. So this IP is available in most TSMC processes, 7 nanometer, 6 nanometer, but all the way to 16, 12, 28, 22, and 40. It supports protocols like LPDDR5, LPDDR4, and 3, and it supports DDR4 and DDR3, and future versions will also support DDR5. It includes, of course, IOs, and licenses are the licenses are for single multi-use with no royalties, and option to license also third-party controllers. Of course, reduce license costs when it's bundled with other TCI timing IP. Okay, so I'm done. Thank you for listening.